Today we are doing something different. We are solving a problem from School of Science and Maths Journal, and the problem is proposed by Tuis Prakash Sharma, India. Okay, so for this problem, we are basically dealing with gamma functions in the end. But before that, we need to know some concepts about real part and imaginary part and how do we deal with them. We know e to the power I theta is cos theta plus I sin theta, and the real part of e to the power I theta is cos theta, and the imaginary part of e to the power I theta is sin theta. Okay. Now, we also need to know how do we deal with this real part function. If we have real part of something divided by other function that give real values, let's say we have ln x where x is defined from 1 to infinity. So in that case, ln x will always give real numbers as its output. So this real part function can be extended to cover the e to the power I theta over ln x. So this can be done. And the other thing that can be done is also we can add with some other functions that are seeking for real part. But let's say sin x. So this can be added as well to give real part of e to the power I theta over ln x plus e to the power I theta over sin x. So these manipulations can be done, and we are going to use them in the solving of problem in problem solving. Okay, so now we are heading towards problem. So for this one, we will first make the change. Instead of cos, we are trying to bring e over here because dealing with e is a lot easier than cos. And real part of e to the power I times this thing over here, ln of x square by x square root ln x dx. We will first just deal with this function only. We will name this as I1, this integral, and this integral as I2, and what we are asked is just I1 square plus I2 square. If we solve this one, this will just be similar. It's just that it's a real part of e to the power I ln x square, and sine is just imaginary part of e to the power I ln x square, and the process will be similar. And now we can bring real part to cover the denominator as well. E to the power I ln x square by x square root ln x dx. Now since integral is actually a sum, so we can also bring it here, as we earlier saw that real part is linear, so we are using the linearity of real part to bring it out of the integral. So now we are seeking for the real part of the integral that we found out here, okay, real part of the integral. And now this is just e to the power ln of x to the power 2y. I can be taken over here, and then e to the power ln will cancel, so we will have x to the power 2i by x square root ln x dx. Now we can bring all of them to the numerator. A real part of integral from 1 to infinity, that's x to the power 2i minus 2, and ln x to the power minus 1 by 2 dx. Now instead of dealing with ln and x, dealing with e and x will be easier, so we will say y equals to ln x, so that e to the power y equals to x and e to the power y dy equals to dx. And if we make the change y equals to ln x, we will also need to make the change in the limits of integration. For 1, x being 1, y will be 0, ln of 1 is 0, infinity, y infinity. And now this is e to the power y real part of integration from 0 to infinity, and this is what was it, e to the power, okay, let me just remove this one, and this is e to the power y, this is bracket, times 2i minus 2, this is y to the power minus 1 by 2, and dx is e to the power y dy. Now we have real part of integral from 0 to infinity. This will be e to the power 2i minus 1 y to the power minus 1 by 2 dy, and this is real part of integral from 0 to infinity. We have y as well, e to the power minus of 1 minus 2i y to the power negative 1 by 2 dy. Now you might have a curiosity why I changed the order of the terms over here. This is because we have a standard formula of this kind that's related with gamma function. So gamma of x is integral from 0 to infinity e to the power minus t to the power x dx. So this is gamma function, but here we don't have exactly negative t such thing. Here we have negative something times y. So let's see a case where what happens if we have e to the power negative st and then t to the power x dx. For this we can just let y equals to st, then we have dy by, sorry, this is dt not dx, this is actually dt, x is a constant over here, so we get gamma of x, this is dt, I'm sorry for that, and now we have dy by s equals to dt. Yeah, then we have the limits will again be 0 to infinity and e to the power minus y. Here we have I have done another mistake. This should be negative x minus 1. I'm extremely sorry for that. E to the power minus 2 e to the power x minus 1 dt is the definition of gamma of x. Sorry for that. And here we will have y by s to the power x minus 1, and again here we will have dy by s. So you see that we will have we have s to the power x minus 1 over here and s over here, so that will be s to the power x minus 1 plus 1, and integral is from 0 to infinity e to the power minus y to the power x minus 1 dy. So this is again gamma of y, so we have 1 by s to the power x, so this is gamma of x, so the result is gamma of x by s to the power x. Yeah, I hope you got it. So when in this case when we have a minus of st, in such case we have the result will be gamma of x by s to the power x, and in this case s is just 1, so we will just have gamma of x. I hope you got this result. If you have, I will just erase this. Okay, now we know that integral from 0 to infinity e to the power minus st t to the power x dt is gamma of x by s to the power x. Now for this one as well, this will be real part of again 1 x minus 1. Yeah, now this is just 1 by 2 minus 1, so this will be gamma of 1 by 2 over 1 minus 2i to the power 1 by 2. Okay, so now we need to find real part of this function, and it's not that hard actually. For that, we can just take first gamma of 1 by 2, that's root pi outside, and then real part of for this, we will first write it like this. We want it to be numerator and not denominator. Now we can just do some rationalization kind of thing, so that we will have 1 plus 2i over 5. Yeah, we just multiplied numerator and denominator by 1 plus 2i. Okay, and after this, we can just take again root 5 out, so we will have root pi over root 5 outside, and then real part of 1 plus 2i to the power 1 by 2. Now you can just find its square root. Or you can also go some other ways. First of all, we can try to make this as cos theta and sin theta. Okay, so for that, we have root 5 over root 5, and we need to introduce over here root 5. Yeah, because we have 1 square plus 2 square as root 5. So if 1 and 2 are perpendicular in bases, then root 5 will be the hypotenuse. So this can be sin theta and cos theta in that case. So we can introduce 1 root 5 in the for both the terms, so that this is sin theta and cos theta simultaneously. And if we do that, we also need to have those cancellations. So we will write 5 to the power 1 by 2 to the power 1 by 2, that's 5 to the power 1 by 4 over here. Yeah, and now we have root pi, and if we bring it out, we will have 5 to the power 1 by 4 in denominator, and real part of 1 by root 5 plus 2 by root 5i to the power 1 by 2. Now, this can be said when 1 by root 5 is cos theta, 2 by root 5 will be simultaneously sin theta, and we will use that. So this is root pi by 5 to the power 1 by 4, real part of let this be cos theta plus I sin theta to the power 1 by 2. And now in this form, the power will just come directly at the angle. That's De Moivre's theorem. De Moivre's theorem said that if it's cos theta plus I sin theta, we have this. Then if we are doing any nth power, this will be cos n theta plus I sin n theta, where n can be any real number. So we will use this formula from De Moivre's, and we will get real part of cos theta by 2 plus I sin theta by 2. Okay, now our real part is just cos theta by 2. So the answer of the integral is root 5 by 5 to the power 1 by 2 cos theta by 2. But now we need to find cos theta by 2. Yeah, so cos theta by 2 we know is root under 1 minus cos theta over 2. And what's our cos theta? 1 by root 5. Yeah, 1 by root 5. So 1 minus 1 by root 5 by 2 is our cos theta. Okay, and now this will be root 5 minus 1 by 2 root 5. So our integral is root 5 pi by 5 to the power 1 by 4, and root under root 5 minus 1 by 2 root 5. This looks messy, but this is not what we are asked. We are asked I1 square plus I2 square. Now let's also try to find I2. For I2, you know that the only thing we need to do is here we will have imaginary part e to the power IRN square. Sine is just imaginary part, and imaginary part, imaginary part, imaginary part, imaginary part, and it's continuous. And here we need to have imaginary part over here, that's sin theta by 2. Oh sorry, for cos theta by 2 it's plus over here. Yeah, and now for sin theta by 2, we will have minus over there, and that's the only difference. Yeah, so we know that when it was minus, we got something like sine theta by 2 is equals to root under root 5 minus 1 by 2 root 5. So this is sine theta by 2. And our I2 will be, just we need to have your sine theta by 2 instead of, yeah, because this is the imaginary part. So for imaginary part, we will have your sine theta by 2. And this is the I1. And our I2 will be root pi by 5 to the power, 5 by 5 to the power 1 by 4 root under root 5 minus 1 by 2 root 5. Okay, so now we are going to have to add them, I1 square plus I2 square. So I1 will be now pi by 5 to the power 1 by 2 root 5 plus 1 by 2 root 5 plus I2 will be pi by 5 to the power 1 by 2 root 5 minus 1 by 2 root 5. Now you can take pi by root 5 common, and we have root 5 plus 1 plus root 5 minus 1 by 2 root 5, and there is a nice cancellation, and also we have a nice division as well. We have 2 root 5 by 2 root 5, that's 1. So we have a good, nice concise answer, pi by root 5, and that's what we were seeking. So we have solved this problem from Journal of School of Science and Math, and it was a really elegant solution with gamma function. We just need to have be able to identify real part, imaginary part, and have a little idea of gamma function. That was it. I hope you enjoyed the solution. Thanks for watching, and do check the journals and the problems over there. They're really interesting. Yeah, see you next time in the next video. Thanks for watching.